Hi, everybody. Thank you for waiting. Starting my camera here. All right, I think we're going to begin the webinar today. So hi, everybody. Welcome to today's webinar. My name is Eric Bitmanis. I'm the Business Development Specialist here at Canary. From Canary, I have joining me today Tom Vitez, our Senior Director of Applications, and Annie Jolicoeur, our Program Operations Coordinator. And of course, from CENGN, I also have Peter Heath, who's a Senior Manager of Training Programs. We are recording the presentation today, and it will be available on YouTube shortly after the webinar concludes. We did send out the PowerPoint slides earlier today as well, so if you would like to follow along there, you're more than welcome to. And if you'd like to ask a question during the presentation, please use the Q&A panel you see on the Zoom interface. Peter will have a couple spots in his presentation where we can answer those questions for you. So feel free to ask them as the presentation goes on, and we'll get to them when we get to those spots. Now I'd like to hand it over to Annie Jolicoeur, who will do this introduction in French. Annie, please take it away.
Bonjour à tous et bienvenue à ce webinaire. Mon nom est Annie Jolicoeur, je suis coordonnatrice à l'opération des programmes chez Canary. Avant de commencer, nous tenons à vous aviser que ce webinaire est enregistré et il sera rendu disponible sur YouTube par la suite. La présentation PowerPoint utilisée pour la présentation d'aujourd'hui devrait vous avoir été envoyée par courriel. Alors, si vous voulez suivre sur votre propre copie, sentez-vous bien à l'aise de le faire. Si durant la présentation, vous souhaitez poser une question, s'il vous plaît, utilisez la fonction questions et réponses, donc le Q&A du menu au bas de votre écran. Et Peter va y répondre lors d'un des moments prévus à cet effet durant la présentation. Je redonne donc la parole à Eric pour la suite du webinaire.
Thank you very much, Annie. Going to begin the webinar. Here we go. So going quickly through today's agenda, we just went through the welcome. We're going to have a couple updates about the DAIR Cloud program before getting into the machine learning presentation done by Peter today. And then we'll finish off today's webinar with some closing thoughts. So updates going on right now with the DAIR Cloud program. As we mentioned in our last webinar, we did announce that we selected 4 new booster packs for production: smart contracts, blockchain DLT with Hyperledger Fabric by Sanofi, cloud-based platform for geospatial intelligence with machine learning by Ecosystems Information Inc., automated static and dynamic application security testing by Parabellix Corporation, and advanced data analytics using AI by Intellis AI. While we did announce the selection of those booster packs in our last webinar, we are happy to report that 2 of these booster packs are very close to the end of their production, and they will be available soon in our booster pack catalog. Those booster packs are the smart contracts, blockchain DLT with Hyperledger Fabric by Sanofi, which we do have the next webinar scheduled for March 23rd. So I will have more information on that later in today's webinar. And then the other booster pack that is close to finishing production and being available in the catalog is automated static and dynamic application security testing by Parabellix Corporation. And we expect to see that booster pack in the catalog sometime in April. And we'll have more information on that later in the presentation, as well as in the weeks to come. So without any further ado, I would like to welcome Peter. Peter Heath is the Senior Manager for Training Programs with CENGN. He has spent over 2 decades in ICT-based higher education and commercial training, teaching courses at all levels, developing commercial training content, and leading programs in college and industry settings. Peter enjoys all kinds of technologies, all kinds of sports, and many years ago, he earned a PhD in mathematics. So please take it away, Peter.
Thanks very much, Eric. And welcome, everybody. It's good to be with you today. I did notice a couple of the booster packs that were discussed on a slide a couple of slides ago actually mentioned machine learning and AI. So it's kind of cool that we're able to link that and help to explain what we're doing when we talk about machine learning. CENGN is, of course, Canada's Center of Excellence for Next Generation Networks. We have 2 ways that we help people and companies in the Canadian tech ecosystem commercialize their products and services better. First, we work with small or medium enterprises on validation projects. And what I've done here is just gone to our website, CENGN.ca, and there's a whole list of CENGN projects. And if you get to this page and just select on artificial intelligence, you can read about some of the interesting companies that have AI and ML centric products and services that have done some of these validation projects with us. We also have a training program because a lot of companies are working in truly cutting edge areas where it's really hard to find the skills they need in order to grow their companies. So that's where our training program comes into the mix. And what I'll do is actually one thing, let me get my slide deck going because everybody needs a slide deck. We laugh about that, but honestly, I just feel much more comfortable with a slide deck and it's horrible. But there you go. A little bit of an introduction to machine learning for the next hour or so. What we're going to do this afternoon is talk about some of the key concepts that you need to understand before digging any further into machine learning. What is it? What is it not? What is it attempting to do for us? We'll look at a particular paradigm called supervised learning and investigate a couple of supervised learning models. And then we'll do a bit of a live demo where you can see how we would build and validate a supervised learning model in the real world. So, foundations of machine learning. Now, I think we all have a sense that machine learning is all around us, but it's interesting to step back a little bit and think more clearly about where we actually find machine learning. We find it in targeted advertising. So you're on a website, you're on Google, you're searching for something, it is throwing ads at you. And it's not only based on your search results, but also the kind of ads that have been relevant for people with profiles like yours. That's machine learning. Spam detection is another form, another good use of machine learning, because the specifics of spam change over time, but machine learning models can keep recognizing the characteristics of spam, even as those things morph and change over time. Cybersecurity, lots of websites actually use machine learning to identify click patterns as humans or web crawlers to stop them from harvesting confidential or sensitive data. Medical research, scientists employ machine learning algorithms to search for patterns in genetic sequences of patients to help identify subtypes of diseases. Predictive maintenance, when you're using heavy machinery, it's helpful to be able to schedule maintenance when you really need it. And using machine learning algorithms can help you fine tune what could be a bit of a static maintenance schedule to something that is really targeted to your use case. Document scanning, when we see lots of organizations scanning just warehouses of paper documents into electronic form, and that is a current thing that's going on. But you also want to be able to harvest what is important data out of those documents. And if, machine learning can help you there because you don't have to necessarily tell the machine learning algorithm what to look for. It will just go and find the interesting patterns in your data for you and in the documents. And finally, this actually refers to a couple of companies that are on our website. Market trend analysis. So as you see, perhaps in the restaurant industry, you see trends developing. Machine learning can view those and pull in what's relevant for you. And then you can see where food interest trends are going and get ahead of the curve so that you can be where people want to be 6 months from now. And there's all kinds of things going on with smart agriculture. That is a huge industry these days. So machine learning is all around us. What is machine learning? Well, machine learning refers in general to a bunch of different computer algorithms that use statistical reasoning to find patterns within massive amounts of data. Now, an important part of this to keep in mind is that your machine learning algorithm is not a static algorithm. It's going to do some learning on its own. And it's going to look for patterns in the data and quite often try to make predictions out of that data. Your data can be quantitative, a lot of it is, but it can also be text-based. It can be image-based. It can be audio-video-based as well. Machine learning algorithms can work with any kind of data, anything that you can store in terms of data. You can find machine learning algorithms that can help you find what's meaningful in the data that you've stored. Machine learning is not a couple of things. So as I said before, it's not a static rule-based method. It's not a simple computer program with a whole lot of if-then-else statements. That could be very useful in a lot of situations, but it's not machine learning because there's no learning. Everything is hard-coded and advanced. And it's not simply descriptive statistics. So at the bottom, we can see 3 boxes representing, understanding that you might get out of data. So hindsight, insight, and foresight. Hindsight is where descriptive statistics kind of live. You're looking for patterns, and all you're trying to do maybe is categorize and analyze what's happened in the past and maybe present it in an interesting way for business and organizational leaders. But that's not machine learning typically. Machine learning enters into the picture when you try to move from simply looking at the past to the present. What insight can I gain right now? How can I make sense out of all this data? And then foresight, prediction, dynamically preparing for the future based on the insights. Machine learning algorithms play a major role when you have moved out of hindsight and into insight and foresight. So again, machine learning, it is computer algorithms, lots of statistics involved, but they learn and they change. They're not simply hard-coded rules. There's a number of, I'll call them paradigms. You could think of them as different kind of categories of things you can do or algorithms in machine learning. There are 4 main ones: supervised learning, unsupervised learning, semi-supervised learning, which is kind of a mix of the first 2, and then something called reinforcement learning. Now, each one of these, we could spend an entire afternoon talking about. So for the sake of this webinar, we're going to just talk and introduce supervised learning and unsupervised learning. And really, these are the most common types of algorithms that you'll find. So then, what is supervised learning? Supervised learning is an algorithm that uses labeled data. So by that, I mean a label that's got a collection of inputs and some kind of an output. And by the way, when we talk about inputs with machine learning, those are typically called features. And then the output is going to be this thing called a label. What a supervised learning algorithm will attempt to do is learn the relationships that drive this collection of inputs to be, or this collection of features to correspond to this label, so that you can then introduce new data points that don't have that label and predict what the label should be. So, for example, what we're showing in the graphic here is a bit of an image recognition problem. We've got a number of, perhaps they're photographs of fruit, and they're labeled. So you've got photos of apples, each one is labeled as an apple. And then everything is labeled as, well, in this case, maybe just not apple for simplicity. Your supervised learning algorithm will make the connection between, what is characteristic of an apple with the label apple, and then everything else is not an apple. The goal then would be to feed this algorithm new photographs, and then it should be able to figure out, hey, this is an apple or this is not an apple. So it would be applying the label based on the characteristics of the photograph, all the inputs, all the features. On the other hand, unsupervised learning works with unlabeled data. So a goal here is to infer some kind of natural structure present within the data without the data scientist telling the algorithm in advance what to look for. So you're going to be grouping similar observations. And of course, then you still want to be able to apply that to new data points and get them into the correct groups, but you don't know what the categories are. You haven't kind of called out, what category A is and what category B is. You're letting the algorithm do the work of figuring out, what's common here and what's common here. So then you can actually do image recognition with unsupervised learning algorithms as well. For example, if you just have the photos, but you haven't labeled them as apple or whatever fruit it is, then you're going to be working with an unsupervised learning algorithm. And the idea is that the algorithm will learn and identify what's characteristic of an apple. So it's fairly round. Quite often it's red. But then there's also bananas. Bananas typically are yellow, and they have a very distinctive shape. And then there's pineapples. So pineapples, yellow again, but a totally different shape, and quite often with this green stem thing on the top. So just by being able to recognize the patterns and group similar observations, the unsupervised learning algorithm can group all the apples together. And it could tell you, you've got a whole lot of apples in here and very few bananas and just a couple of pineapples. So again, supervised learning works with labeled data. Unsupervised learning works with unlabeled data. And, kind of more broadly, we can think about this kind of a setup for characterizing supervised and unsupervised learning. So if we look first over at the left side, supervised learning, as we said, works with labeled data, which means it's often used for some kind of task-driven project. I'm the data scientist. I know what I'm trying to get. So, I'm trying to predict labels at the end of it. There's a couple of types of algorithms within supervised learning. So classification is great when you have a categorical target. So again, where we had apples versus not apples. Regression is good when it's all numerical data and there's some kind of a continuous target, more of a mathematical approach. And I think my screen got a little goofy there. Okay, on unsupervised learning, again, unlabeled data, and this tends to be more data-driven. Let's let the data talk for itself. And within unsupervised learning, a couple of key algorithm types are clustering and association. So the image recognition problem that we just looked at, that's clustering, where we're looking for objects that kind of look the same. Association is a little bit different. So for example, an online store may know or may have learned that people that buy, 2 pizzas, or okay, let's talk about a pizza shop. They buy 2 pizzas. Very often they may want a bottle of pop as well, and maybe, some dessert. So that's what I mean by an association, associated purchases. So if someone then is onto a website and they're purchasing 2 pizzas, they may get asked automatically, hey, do you want a bottle of pop? What else do you want? Because it's learned the kinds of bundles of purchases that people make. So that's association. Now, your data is super important. If you don't take care of your data, then deciding what algorithm to use is really kind of a waste of time. There's a whole data preparation phase that you need to go through. The first phase is actually, of course, collecting your data. Now, every organization is already collecting data, whether they realize it or not. But it's important to understand what data is important to you. That can be a strategic decision. Now, granted, storage is cheap, so it's okay generally to keep more data than you actually need. But it's very important to be strategic about the data that you're collecting and keeping. Once you have your data available, you then need to check the formatting. So your data may be spread across multiple locations and various formats. So for example, dates. Dates can come in all kinds of different formats. It could be month, day, year. It could be day, month, year. It could be year, month, day. You need, if you've got date features in your data set, you need to make sure that all the data is formatted in the same way. Similarly, if you're measuring things, you want to make sure that all the measurements for a particular feature are in the same units. So centimeters and millimeters, you need to pick one. Centimeters and inches, you need to pick one. Otherwise, you won't get the results that you're looking for. And finally, data pre-processing. So this is where, people often think of the word data cleaning, and this is now the phase where data cleaning appears as a part of the whole data pre-processing phase. So in particular, you may have 500 observations about something. If a few of the data points, whoops, pardon me, are missing a couple of features, you need to deal with that somehow. A simple approach may be to just remove the data points that are missing the particular features. There are other possible approaches as well. You could insert an average value, for example. And then another one is dealing with outliers. You may have one observation that is just utterly different than everything else that you have. You need to deal with that somehow. Otherwise, it could skew your algorithm. So data collection, data formatting, and data pre-processing are all important. Also, you need to validate your model. And this is particularly true in supervised learning models where you're trying to make some kind of a prediction. And one of the issues here is how to use your data. So you've got lots of data. If you use all of your data to set up your model, they say train your model, and then you try to validate it against the same data that you used for training the model, it should work pretty well, right? You're not going to get any surprises there, but it doesn't mean that it will work for new data. On the other hand, you could use all of your data to train your model and then find similar data somewhere else to validate against, but that can be costly, not only in terms of purchasing the data, but you then have to make sure that this new test data is set up the same way as your training data was. So a typical approach is to take your data and split it into a training set and a test set. And in fact, you should do this multiple times. So here's a way that you can do exactly that. Let's say that we've got 3,000 past customers and we want to make some predictions about future customers' behavior based on past customers. A simple way to estimate the accuracy would be to randomly split the sample of data into 3 parts. Those are also known as folds of 1,000 customers each. And then you run the training of the model and then testing 3 different times. So in round 1, we take fold 1 and fold 2 to train the model. And then we test it on fold 3. And then we do round 2. That's fold 1 and 3 for training, and fold 2 for testing, etc. And the reason you want to do it multiple times is so that you can get some error calculations for each round and average those. Because it's possible that just randomly you got in the first round, just randomly you picked like a perfect way of splitting the data, and it appears that the test data lines up 100% with that, but it's probably not really accurate. So doing it a few times with different splits of the data can be a healthy approach. Also, you need to be aware that there's always some amount of error in your model. And there's two main types of error that we need to talk about. One is called bias, which is the blue curve, and the other one is called variance, which is the orange curve. So bias refers to how accurately your model fits the training data. Forget about the test data. So a model with 0 bias will fit the training data perfectly. And that's out to the right where the blue curve goes down. High bias, however, means the model does not fit the training data well at all, and that's to the left side. And an interesting thing to note here is that high bias typically doesn't come because you don't have enough data. It's because you're working with a poor selection of model. So bias. Variance is a different kind of error. Variance refers to the sensitivity of the model to the data it is trained on. So if the model changes drastically, it changes its predictions drastically when new data points are introduced, then the model is said to exhibit high variance. Now, both high bias and high variance lead to high prediction error and poor model performance. So simple models tend to underfit the data, as you can see on the left side. They have high bias, but low variance. Complex models typically overfit the training data. They kind of absorb all the noise in the data a little bit too well. And they suffer from low bias, but high variance. So what an excellent data scientist will do is find a balance between these two types of issues in model. I'll also note that you need to keep in mind that when you're dealing with more complex models, it could lead you to needing greater computational requirements. Another thing is that when dealing with machine learning, a basic principle is that a data scientist should be able to explain the meaning of the results clearly to a layperson. So if you get into a deeply complex model, it may be extremely challenging to explain what the model has just predicted. So we looked here at, again, we've got supervised and unsupervised learning models, task-driven labeled data, trying to predict outcomes, versus unsupervised, which is data-driven, unlabeled data, and you're often clustering observations or looking for associations. You need to prepare your data carefully through collection, formatting, and pre-processing. You need to make sure that you validated your model carefully and take care of the different issues between bias and variance. Now, before we jump into a little bit more about supervised learning, do we have any questions, Eric?
Yes, actually, we've had a few come in so far. The first one I'm seeing is a bit about paradigms. So we talked about supervised learning and unsupervised learning.
Yep.
But Bruce has brought up self-supervised learning. Does that fit into, like, example being GAN frameworks? Is that fitting in under the supervised paradigm, or is it a little bit separate?
That's a good question. What I'd like to do, if you don't mind, if you can toss me that question afterwards, and I'll make sure I get the clearest answer that I can. And then we can send that back out to all the attendees.
Sounds good. Okay, I can definitely do that. And the other question I've had that has come in so far is for data prep in regression type problems, go into a little about the importance of scale and upsampling.
Yeah, scale is super important. So what can happen is you might have one feature that is measured in, let's say, a distance like a kilometers, and then a second feature is actually measured in millimeters, centimeters. So the scale is way off between the two. And that can actually produce some really weird effects in the model. So one thing you can do there is work, like introduce a logarithmic function. So for the kilometers based feature, if you use a log base 10, for example, that gets the number that you're dealing with more in line with the centimeters measurement for the other features. So that can be very helpful. If you've got two different features that are wildly out of whack in terms of scale, that will have some impacts on your model performance.
Perfect. Thank you for that. And do we have time for one more question? We had another come in as well.
Yeah, I think so.
Okay. We have a question here that says, can you talk about the strategies processing data that goes into ML using large data sets versus small data sets, maybe synthetic data?
Okay, so it's better. More data is better than less data, definitely. It's really hard to kind of make a definitive statement about you need this many observations, but generally speaking, more is better. Because if you have any, outlier-ish observations, they can be kind of drowned out simply by a mass of having more observations that are kind of like where you expect them to be. And I'm kind of waving my hands at what I mean by that. The other thing, though, is within large data sets. So first of all, let's talk about just the number of observations. More is better. But in terms of features, it can easily be the case that some of the features, some of the inputs that you're looking at are actually kind of correlated together somehow. So broadly speaking, with human beings, height is somehow correlated with weight, broadly. So if in a particular data set you found out that you did not need to use both height and weight in order to get a working model, then you can eliminate one and still get good performance. And the benefit here is that, there's two benefits. One is explainability, because you're now looking at fewer variables that actually have an impact on the result. The second one is computational requirements. Fewer data, fewer columns in your matrix, if you want to think of it that way, requires less compute power.
Perfect. Thank you for that. We do have some more stuff coming in. Actually, one was a comment from Patrick, says that he uses SMOTE SMOT for synthetic data, and it works well for both R and Python.
Okay.
And the other question actually was just, I'm not sure if you'll answer this later in the presentation, but in terms of workflow tools for building repeatable processes, do you have any recommendations?
That's a great question. Yeah, that is an awesome question. So I think we'll get a partial answer when we get into the demo. But that might be something to take up later as well.
Perfect. Okay, I'll keep those two for later categorized so we can readdress them. Thank you, Peter.
Yeah, great, thank you. Okay, so a little bit more about supervised learning. So each type of algorithm has kind of a characteristic project pipeline. So we talked a little bit about bits and pieces of this before, but now you can see it all in one workflow. With a supervised learning project, the first thing you need to do is collect and prepare your data. And remember, supervised learning needs labeled observations. So deal with the data first. Step 2, split the data into a training set and a test set. Step 3, train the model. So use the training set to train your machine learning algorithm. And then step 4, you're going to evaluate your model with the test set. So remember, you split the data to probably something like 2/3 for the training set, 1/3 for the test set. You run your algorithm using the test set, and then you compare the predictions to the actual labels. And you're going to generate some statistics that are going to be helpful for you to decide if this is a good model or not. And again, like I said before, you want to run this a few times in terms of the training and test set split, so that you didn't accidentally run into a random split that gave you 99% accuracy when in fact it's not really that good, generally speaking. But this is the typical model. So collect your data and pre-process it, split your data, train the model, evaluate the model. 2 algorithm types, and we saw this back on the big kind of flowchart tree, I guess, slide. For supervised learning, 2 important learning algorithm types are regression and classification. So regression works when you've got quantitative data only. So I want to predict a house value based on the number of bedrooms, distance to the school, etc. And a couple of significant algorithm types here would be linear regression. And if you did any statistics in your past, then this is exactly what you might remember. It's basically linear regression. But you can also work with a regression tree that is going to perform predictions by splitting the data into a tree structure. Another supervised learning type is classification. So when you've got qualitative or mixed data, then regression won't work at all. And you can use classification. So you're often trying to categorize data. So you can predict if a credit card transaction is legitimate or fraudulent, for example. Or you may be trying to predict if different customers at your bank, how likely are they to default on a loan? Those kinds of classification type of problems. So logistic regression is a great algorithm when there's probabilities involved. And support vector machine is what we're actually going to look at. So if you have the slides, you'll notice there's a slide here about logistic regression. I'll leave that for you to read. And we'll jump over to support vector machine. So a support vector machine is going to separate data points into classifications. So classes or categories somehow. And it's based on some kind of features in the data. So here's an example that we can see here where we're trying to divide a bunch of 2-dimensional data points into, well, blue and red. You can see that we've already colored it, but there's a reason for that. What the support vector machine is going to find is the best dividing line with the largest supporting margin. So in the diagram, it's pretty clear that I could have a downward diagonal line that would divide between red and blue. I could have an upward diagonal line that divides between red and blue. And those are great, except that what I really want to do is introduce new data points where I don't know if they're red or blue and get the algorithm to categorize them properly. So my algorithm is going to put in a straight line and keep working it around until we've got the biggest margins on either side of it up to the nearest data point in the 2 classes. So here above, you can see there's a blue dot with a black circle around it. That's the closest blue data point. And below it, there's a red one as well, the closest red. So you're trying to maximize this margin. And that margin is what's called the support vector. Mathematically speaking, it's supporting the margins. So you're trying to maximize that margin or that support vector, and that's where the algorithm gets its name. So basically, you're trying to find a way to categorize them that emphasizes as much as possible the differences between these classes of objects. Now, this is the simplest possible diagram that we could show, but support vector machines are much more flexible than this. So it can work with curves instead of lines. It can also work in multiple dimensions, much more than simply 2 dimensions if required. And we're going to see that in the demo in a couple of minutes. To evaluate your classification model, there's a couple of tools here. There are many tools, but we're going to take a look at 2 in particular. One is called a confusion matrix, and below it, there's an accuracy score. So in our confusion matrix, we've got a 2x2 matrix, and we could think again of this kind of situation where we've got 2 classes in our classification. And for this description, we'll not say red and blue, we'll say positive and negative. So like 1s and 0s. So each of the columns represents the predicted value being 1 or 0 out of the algorithm. And then the rows are actual values for the labels 1 and 0. You want to correctly predict the 1s, so true positives. You also want to correctly predict the 0s. Those would be true negatives. And this is a very nice kind of, I'll say, graphical way of displaying how well your model has worked. So you really want high numbers, good performance on true positives and true negatives. There's also false negatives and false positives. You want those to be low in occurrence. And then your accuracy score, that's your first level of a statistic that's going to give you some idea of how well your model performed. And it's very simply true positives plus true negatives over all the predictions. And of course, you would like this to be close to 100%. There's a couple of other types of errors, specific things about false positives and false negatives. I'm going to leave this for a minute. We're going to jump over to the demo. And if we have time after the demo, then we'll come back and talk a little bit more about false type 1 errors, false positives, and false negatives, and a couple of measurements called precision and recall. But for right now, let's jump over to a lab demo. So what you're seeing here, this is a very nice tool for machine learning, which is called a Jupyter Notebook. A Jupyter Notebook, it's a web-based open source user interface where you can build code from Python and some other, I think Ruby is one, and there's some other ones that are easily usable in a Jupyter Notebook. And you can then run the code and see the results. It's a very nice tool to use. So what we're going to do is implement a classification, a support vector machine model to classify tumors as either cancerous or not cancerous. And there's a number of steps that we go through, which are a little bit more detailed than the workflow that I showed you before, because some of these steps are more specific to the programming and coding part of it. So the first thing I need to do, oh, by the way, we are working with Python, in case I forgot to mention that. Python is really big in machine learning because there are just lots and lots of freely available libraries with pre-written code. So instead of having to write your own code for a different machine learning algorithm, you just import it and it's ready to go. So we do some importing. Next step is to import the data set. In this case, this is a CSV file. And I'll mention right up front that this is a publicly available data set. So next, you want to take a look at your data. A bit of a visual inspection is always a great way to start. So here we go. We see the first 5 rows of the data set. And you can see that there's an ID column from the original experimentation, and you can see people's names. So I just wanted to let you know this is a public data set. You might also think that these are not really important if we're just trying to figure out if different samples are cancerous or not, and you would be right. So there's a number of tools in the Python toolbox. Describe will give you a nice statistical summary of the different features. Info gives a different way of looking at the different features. And I'll point out something immediately for you to look at here. So besides the variable type, what's important to note here is that on the radius, there's a whole lot, there's 71 observations that are missing the radius feature. So that's going to be a problem that we'll have to deal with. Okay, into cleaning the data. So the first thing we're going to do is drop the ID and the name. We don't need those. And then we'll just quick use the head function to check that those were dropped. Yes, they were. You can also see immediately that even in the first few rows, we've got some radius entries that say NaN. That's not a number. And that's where we're going to have a problem in a minute. So what we can do is use a pre-written function that will just drop all the rows that are missing any numerical features. We check, they're all gone, and we can do a visual inspection again, and you can see now, previously there were a number of, just in the first several rows, that were missing the radius. Now, everyone that we see has a radius entry. The next thing we need to do is define the variables. And what I mean by that is what's the label and what's not. So the diagnosis, that is, of course, the label that we're interested in. So we're going to define that as the label that we want to be able to predict. And we then make X the whole data set except for that column. And now we're going to split the data. So again, Python is great. Here's a pre-written method that can split the data into a training set and a test set. So the test set size is going to be 30%. It does it randomly. So depending on what number I select here, I'll get a different mix. So let's make sure I do that. And then run the model. So again, lots of libraries available. There's a big library called sklearn. And we're going to import the SVM, support vector machine function or method from sklearn. So it runs it. Linear here means we're using a line. And it's all happened in the background. It happened that fast. So for the sake of time, there's a number of things that you can do to inspect and evaluate visually how the model performed. But let's jump down a little bit and look again at what I talked about, this confusion matrix. So I've created it. That's a little bit hard to see there. So we can actually plot it very nicely using some Python functions. So the actual labels of the data are shown as rows, so benign and malignant, but then the columns are the predicted labels, benign and malignant. And again, the main diagonal is where you want to see the preponderance of the predictions show up. So those are nice big numbers, and that's a good thing. And we can get the accuracy score as well, 94%. So that's very nice. Now I'm going to jump back up because I said before that just doing it once isn't really great. So if I change this random seed to 19, and so now I've split the data again, and I run the model again, and we jump all the way back down to the confusion matrix, and we'll plot it so it looks nice. You can see that the numbers have changed. And in fact, if I run the accuracy score again, it dropped a little bit. So 94 might have been a bit of a high watermark in terms of accuracy. So then if I got this again, here we can see it a little bit bigger. The matrix was a little bit small. So we saw, again, out of 91 observations that were actually benign, the model correctly labeled them as 88 of them as benign. And then 54 out of the 59 malignant observations were correctly labeled by the model. So we get an accuracy of 94%. And then I want to leave some time for questions, but just scrolling back here, false positives and false negatives. Any error is not great, but in some cases, a false positive might be worse than a false negative or vice versa. In the use case that we just went through, trying to use ML to diagnose cancerous or benign tumors, I would rather have a false positive than a false negative, right? Because a false negative means it's actually cancerous, but the model didn't pick it up. So the measurement is called recall. High recall gives you very few type 2 errors. And then if we go back here, recall for benign was 97%, but recall for malignant. So did I really get the like, if you think of malignant as what you're trying to predict, then the recall was only down at 92%. So 8% of the time we were letting false negatives get through. So not, you know, maybe there'd be ways that we could tighten that up a little bit. But that's all there on the slides. You can check that out after the webinar. And that's really it. So machine learning is useful. There's a bunch of different paradigms. Every model has a good end-to-end process. I will mention that this is all a little bit of material taken from CENGN Academy's self-paced online course, Machine Learning with Python. It's got labs set up exactly the same way as you just saw me go through them. There is a digital badge exam that's associated with it. I personally, I think it's a pretty good course. We've gotten some pretty good reviews on it. there's lots of hands-on if you want to dig in and learn more about machine learning. And Eric, that's it.
Fantastic. Thank you for that great presentation. We do have quite a number of questions that have been coming in while you've been talking. The first thing I will read out is it was a comment when you opened up Jupyter. It's a comment that says Jupyter also supports math language Julia and also R. So if anyone is using those languages, I believe then Jupyter would be able to help you out.
Yeah.
The first question I have here is imputation for both outliers and missing values.
Yes. Okay, so that is, there's no simple answer for that. So I mentioned it in our case, we just, missing values, we just got rid of them. You could impute rather the mean value of everything else in that feature. That might actually get you better results because you're restoring a few observations back into the model. Outliers are an interesting issue. If you can figure out, like if you have some background with how the data was collected, you might have some understanding of where those outliers came from and what you'd like to do with them. But in every case, when you've got outliers and missing values, that's where domain knowledge will be really helpful as you decide what exactly to do with it, whether you want to impute or drop, or if there's something else that you can do to treat the issue of those outliers and missing values.
Perfect, thank you. The next question we do have here is, what is more important, model accuracy or model performance?
So if the question asker could just clarify, what do you mean by model performance? I'd be interested to know what you mean in terms of accuracy versus performance. And if we could get that, then I could cycle back to that one.
Okay, I will let you know if he responds.
Yep.
The other one we have here is how about we use F-score rather than accuracy?
So yeah, F-score is possible. There's actually quite a number of measurements that you can use. So one advantage to using accuracy is pretty much everybody understands it. And as an introductory webinar, it's a great way to go. But there's lots of other options in terms of kind of scoring how well, how accurately, air quotes, your model is performing.
Perfect, thank you. While I wait for that other answer on that previous question, we do have a more specific question here that is asking about algorithm selection. So they're asking about if there's no current ML model that is out there to predict flood locations, provided they had all the atmospheric parameters and actual weather data. Where would you start in like an algorithm selection for something, I guess, as chaotic as flood prediction or flood locations?
Wow, that's an excellent question. So I'm interested at the comment that there's no algorithms that will do that. So one thing, so I'm just kind of thinking at the top of my head here. One thing I think I would like to do is actually select the data carefully. So, part of the issue might be that you're taking too broad of a data set. If you can focus it into, some geographical zones that are kind of common, that might help the whatever model you're choosing to work better. I would still tend to, so then you're looking at some elements of a supervised model where you can look at, here are places where we had flood, yes, yes, yes. And you do want to try and predict where you think that they will come with some kind of a probabilistic model, probably. But I would be interested, and I'm a bit of a nerd, I would be interested then to kind of grab hold of the way that the supervised model characterized things and just, kind of compare that to an unsupervised model on the same data, and like just kind of stare at that for a while and see if I can make any sense out of, what is one model type telling me? What is another model type telling me? That kind of a situation would probably, so you might want to, try one, add a little bit onto it. You really want to play around with that for a while to see where you can get. But for me, I would start with some kind of a supervised learning probabilistic model just as a starting point, but not necessarily the end point. Keep working, keep digging, see what else you can add into the model, different, things going on the side that might help you get it more accurate.
Awesome. Thank you so much for that. That was he's saying his appreciation for that. He says, great tips. Thank you very much.
No problem.
We do have a little more information regarding the previous question.
Yeah.
So the previous question was about, just so I can find it here.
Accuracy versus performance.
That's the one. Okay, so for accuracy versus performance, he says there are models with higher accuracy that can perform worse in predictive power. He says, does that make sense?
Okay. So, you know what? So I'd love to have a little bit of a dialogue afterwards, just kind of by email about this question. But from what is being said, it makes me think that the model, like a model, when I say a model performs well, to me that includes a high accuracy score, and the predictive value should work well. So it may be that a model wasn't validated as well as it should have been in terms of like choosing the data. Oh, you know what? So when you're talking about accuracy, so if you're talking about a contained data set, and then you're bringing in new data that you've never seen before, that it is possible that there's stuff happening in the new data that you don't recognize. So what I would tend to do in that kind of a situation, and that this may be where the question is coming from, that I would try to keep retraining the model periodically, bring in some new data, retrain it. Maybe you need to make some adjustments, make it a little bit more complex than it was before. So for example, with a support vector machine, maybe you need to move from a linear model to a curve model because of things that are coming in that you didn't recognize before. So yeah, I would say a key thing is just to keep retraining the model. And in fact, I wanted to mention something that's a great reminder. Machine learning projects should never be static. It should never be, we've got the model, we did it once, we validated it, and that's what we use for the rest of the time. You do want to keep bringing new data into it, retrain the model periodically, because you may have made an assumption that worked for the data set you started with that actually isn't valid once you start bringing in new data. So you keep retraining it. If you have to change it, that's great. You have a new opportunity to make it more accurate, perform better in the field. So yeah, I think if I could say this, I would say, if you find that the model stopped performing well, figure out, retrain the model, make some adjustments, make sure it still works on the original data set and on the new data points that you've introduced. So, it then becomes, kind of a living model, if you could call it that.
Okay, thank you. You did have another little follow-up, which is model accuracy is only a subset of model performance. Am I right?
Yes. Yeah. So in fact, if we go back over here, right, the precision and recall, those are some other elements in terms of, evaluation metrics. So as I was saying, like the accuracy looks pretty good overall, but this last row, pardon me, whoops, where did my number go? Oh, I know where it is. Here we are. 92% for recall on malignant tumors. That's, you know, I would like something that smacked more of 95% 95% performance rather than 92% performance. So yeah, thanks for the clarification. Yes, accuracy, that is just your first kind of very vanilla metric, but you do want to dig in more things like precision, things like recall, other types of metrics as well. So yes, there are other measurements that you can use that really, fine tune it and give you a sense of, yeah, was the accuracy number hiding something? It might have been.
Perfect. Thanks you a lot for your input on that. I do have one comment here. I do need to wrap up as we are going over time. The comment actually related to the flooding solution. It says that for every classical machine learning model, there's a near equivalent neural network that can converge to 100%. So possibly another solution there for our flooding problem. I do want to go quickly through the remaining slides I've got real quick before we wrap up today. So just give me 2 seconds to move over there. As we do have that one remaining question, which was about workflow tools for building repeatable processes and what recommendations you might have. While you mull that over, I'm just going to wrap up quickly here.
Yeah. So Eric, that's one I'd like to have an opportunity again to come out with a good answer. So
okay, perfect. Yeah, we can loop
we'll
that in.
that and respond by email.
Okay, thank you very much. Yeah, we will loop that into the email, especially when we have the recording as well. Realize that my video is not even on. Here we go. So just finishing up today with our closing thoughts as we are over time, but I appreciate all the great questions that came in today. And thank you again, Peter, for the presentation. As you can see, it was not only well received, but very, very, I would say it's a very hot topic for our audience. So this is great. I do want to mention about the booster pack builders that we did mention earlier, and that we do have a couple spots remaining for builders. If anyone here is interested, we're looking at Canadian businesses with experience and expertise in emerging technologies. So if you do have knowledge not only in machine learning, artificial intelligence, blockchain is another one we're still continually looking at. Cybersecurity is another big one. And you are interested in building out a booster pack, you can find out more information on our website. We do offer $50,000 to successful booster pack builders, as well as exposure and recognition to the DAIR user base, as well as the community abroad, and connections to new potential partners and resources. So if you are interested, please check out canary.ca/cloud, and there'll be more information there on how to become a booster pack builder. And it's also there where you can submit an expression of interest for an EOI. And the next DAIR webinar, as I did say, is March 23rd, 2022 at 1 p.m. We do have the registration link in the slides we did send out earlier. It is on the new booster pack we will be releasing, which is smart contracts, blockchain, DLT with Hyperledger Fabric, and that's going to be presented by Sanofi Inc. So please also take a look at your inbox over the next coming weeks for announcements about that webinar and other registration links if you did not download the slides ahead of time. But that is all for today. Thank you very much, everybody, for staying over time and participating here in the DAIR webinar, as well as, again, thank you to Peter for the great presentation. And we'll get you those answers to the questions that you did ask via email that Peter said he would respond to. So we'll probably package that all together with the link to the recording of the webinar as well, if you'd like to revisit this. But thank you again, everybody, for coming today. And that's all. I hope you have a great rest of your day.